Okay, good morning. So we were talking about anomalous phase coexistence. Let me just write down the equations of motion again. Rho dot equals, so this is minus div j, but I can write j as some mobility, which won't matter, times the gradient of a chemical potential, which may not come from a free energy. So this has a local part, and let's put the two terms that we discovered in the previous lecture coming from both the active model and the passive ones. And what I said was, if there's an F, 2 lambda plus dk d rho is equal to 0. So if you like, you can think of that as the integrability condition, which allows you to get from a chemical potential to a free energy. And we're looking for an interfacial solution, which takes us from a low density rho g to a high density rho l, and it's a steady state solution of this equations. So I gave you the reference as to where you can read about this, but my first condition, which is where we ended last time, was to say that the current is going to have to vanish. So this is the divergence of the current with minus sign, unless you have some steady current through this quasi one-dimensional system, which would require very peculiar boundary conditions. So that says that grad mu equals 0, so mu is a constant, and what's more, in the bulk phases, so in the bulk phases where there are no gradient terms, these both have to be equal to that constant, so mu naught at rho L and mu naught at rho G are both equal to the constant value of mu. So that's an equilibrium-like condition, and what we need is the second condition for phase coexistence, which is the equivalent of finding equality of the thermodynamic pressure in an equilibrium system. So I'm not going to, what I'm going to do is just tell you how to do it and then say why this works. So the crucial step is this. We basically end up transforming the variable rho in a specific way. So let me introduce something which, for want of a better name, I'm going to call a pseudo density. R of rho. And this is going to obey the following equation. R of rho obeys K R prime prime. The prime here is R d by d rho equals minus 2 lambda plus K prime R prime. I'm going to give this a star. And you might say, well, why on earth would you want to do that? And hopefully that will become clear in just a moment. So prime is d d rho. So this is a nonlinear transformation of the density to give something called R. And then I'm also going to define the following. So if R was a density, and okay, let's write this down and see where we get to. So this is the definition of a function of R, big phi, and this is defined by d phi dr equals mu naught. Well, mu naught is a function of rho, which is therefore a function of R. So I first find the function of R, I express mu naught as a function of R, and I integrate it once, and that gives me this phi. So that looks a bit mysterious, but then the key point is the following. So notice the following. If I integrate, so this is the x direction, from a point in, I could integrate in either direction, I could have drawn that the other way around. Let's integrate from a coordinate which is deep inside the vapor phase to one which is well inside the liquid. So at both of these endpoints, the gradients vanish. Mu of rho times the spatial derivative dx of the function r dx. So this is the full chemical potential, so that includes these gradient terms here. But the full chemical potential is a constant. So I can also write this as integral xg xl of mu bar, a completely constant thing, dxr, So this is R in the liquid minus R in the gas times mu bar. So I have two equivalent forms here. They must be equal. That thing is a really easy thing. It's R difference times the constant mu bar. So now we're going to work out what the left-hand side is when we put that expression into it. So let's call this 1. So I can rewrite 1 as this, integral xg xl. So we can take the local part of that first, mu naught of r. Well, yeah, I can write this mu naught of r. Mu naught is a function of rho and therefore a function of r dx r dx. And then there's another term here, which, given this equation, takes the following specific form, minus d by dx of k over 2 r prime dx rho squared Frankel box dx. And this is using the Stard equation. So there's a reason why I did this, and that's because this transformation here turns turns the gradient part of that object into a total derivative. So it's like an integrating factor. I find a way of transforming my variables so that the gradient piece of the left-hand side of this equation integrates to 0. It's a gradient, and there's gradients inside. So at both ends, it vanishes. Now, that wouldn't be true if I did this with just rho as the variable, because this thing here is some non-integrable mess. It's the combination of those two terms there. So that choice of r massages the two gradient terms into such a form that when I do this, I get a total derivative. So then I can integrate that using this thing. So this is, so using star, this is 0. So the expression 1 is phi of RL minus phi of RG plus 0. So now I have something which looks very like the equilibrium case, but is in terms of these transformed variables here, because I have the two mu's are the same, and now I have, what have I got? I've got this equals that, so I can also write that in the following way. Phi RL, yeah, just let me do this and you'll see what it looks like. Just writing this out again, mu bar RL minus RG. Mu bar has got to be the derivative of phi, if you think about this equation. In the bulk, that's, if I look at that in the bulk, it has to equal phi prime, because it's mu bar is mu naught evaluated in the bulk, and that's the derivative of phi with respect to r. So finally here, what I have is phi prime r minus phi in the gas phase is equal to phi prime r minus phi in the liquid phase. So let me define this as something we call a pseudo pressure. So this in the gas is equal to this in the liquid. So this is a analytic procedure which tells you how to construct, for this type of system of equations, a steady state that connects two values of the density. And we've got two conditions, that the two densities have the same chemical potential, but we also have this extra condition that they have the same pseudo pressure, which is computed in the way I've decided here. So what we have is equality of chemical potential and pseudo pressure. So another way of saying that is that the common tangent construction holds, not on the function f of rho, but on the function phi of r. And the final comment is that, note, this should be fairly obvious, in equilibrium, so in an equilibrium system I have an f, the right hand side here is 0, so r has no curvature, so it's a linear function of rho, so it may as well just be rho. A rho plus constant, i.e. rho. So this becomes the common tangent construction in the special case where the system is integrable and this object vanishes. So this is the proper generalization of the bit of equilibrium thermodynamics which governs phase coexistence to models like this which don't have a free energy. Yes? Oh, that's a very good question. I don't actually know the answer to that. I don't know if Julian's thought about it. Did you? Yeah. Yeah, my guess would be actually that you'll get corrections from those terms. That would be my guess. In other words, if those terms aren't integrable, so what this shows is that the terms that live here, if they're not integral, in other words, they don't come from free energy, change the answer for the coexistence. And I would expect that to apply to higher order terms as well as the terms we have here. Okay, Julian's nodding, so that's probably the right answer. Okay. Right. Okay, so that's the procedure. And what I'm going to do now is not apply this directly to the model that we had last time for which had rho log rho stuff and integrals of v of rho and stuff here. What I'm going to do is step back from that and introduce a simplified version or a minimalist version of the same type of model, so diffusive active particles, which is going to be called active model B. Okay, so that's the end of the stuff about anomalous phase coexistence. Are there any questions about this before I rub out too much of it? Yeah. We think not. It is, by the way, it is as I mentioned before in Suzanne's talk, there was this funny issue of how you calculate the coexistence between what is the common stress that you need to choose in shear banding, and the analysis by Peter Olmsted of that problem is quite closely related to this. You look at the gradient terms, you do an integral, you see what has to be constant across the integral, and you get a kind of eigenvalue equation for the coexisting things, which depends on the form of the gradient terms. So there is a more general structure behind this. So I don't think that relates to any mechanical pressure. Okay, so minimal MIPS. Active model B. So this model will be directly inspired by the coarse-grained model that we had last time, so it won't be completely general, and we'll come back to that point later on. What we found was, from the microscopics, we have a two-well structure for f of rho, the function whose derivative gives me the local part of the free energy, but that the gradient terms, at least one of them, break time reversal symmetry via not having an f. So exactly like what I've erased here, but a specific case. So what we're going to do is, if you remember what we did in several lectures, it feels like a lifetime ago, I know. Model B, this was in my first lecture. This is a model for diffusive passive phase separation. What we did then was to introduce a variable phi is rho minus rho naught, or rho minus rho c. Rho 0 happened to be the critical density in mean field theory. Phi dot is still conserved, so phi dot is minus div j. And in model B, we said j equals minus, there's a mobility m, which I'm going to set to unity, which I think we even did then. And then there's a noise term, which has a constant coefficient because we deliberately massaged out the multiplicative noise. Here's lambda. Mobility m was beta d and equal to 1. So I still have a noise coefficient which is telling me indirectly about the temperature, so I can think of D as kT if you like. And we chose for f the phi-4 theory, integral a over 2 phi squared plus b over 4 phi-4 plus k over 2 grad phi all squared, square bracket, integrate all space. So that gave us the following mu, so this is just revision. Obviously the mu from model B is integrable in the sense that I described it. K prime is 0 and lambda is also 0, so it's 0. So here's mu, a phi plus b phi cubed minus k del squared phi. So this is the df by d phi. And now I'm going to break time reversal explicitly with a gradient term. And having chosen a constant here, there's a very obvious way to do that. So let me change color and write this in. Plus lambda grad phi squared. So I could make this a function of phi. I chose that to be a constant. If I choose a constant here, it's fine, because this already breaks the relation that an equilibrium must have between 2 lambda being the negative derivative of this k. So I'm going to call this mu active, or mu A. So the chemical potential, now this is active model B. So to out model B in the chemical potential, I've added a term that breaks detailed balance and is of the form that we had popping up in the microscopic model when we coarse-grained it effectively. So just to make that explicit, 2 lambda plus k prime is 2 lambda, is not 0. No F, no global free energy, so yes, not time reversal symmetric. Okay, and I do have anomalous coexistence, obviously, because this is a model of exactly the form I just wrote down. So the problem I was just solving, I did it with rho as the variable, but I can just shift rho by an offset. That's the only difference between rho and phi in the maths we've got here, and do the whole thing again. So I won't do the whole thing again. You might, if you want to do problem 5. But given what I've told you, this is strictly an exercise. I'm not sure that this has ever actually been published on this model done this way, because we originally calculated it in a slightly more pedestrian way before this general structure that I've told you about came to light. So what we can do is you can do the anomalous coexistence, so you can do the common tangent on the appropriately constructed phi now, and then you can just transform back to this small phi. So obviously that big phi is a potential, it's nothing to do with this small phi here. So if you take the result and transform it back into the usual way of thinking, which involves f and rho or phi, equivalently phi. So here's the outcome. So these board erasers are making an incredible mess at the moment. So what I mean by the outcome is common tangent construction on an appropriately constructed phi of R, transform back into f of rho language, or f of phi, excuse me. Can't write at all today, language. So here's f, 2 symmetric wells as ever. So you get a coexistence condition, phi 1, phi 2. And what happens is this. The chemical potential is not changed by the transformation of variables, so they still have the same slope. And this slope would be 0 in equilibrium because the common tangent would just be across the bottom. And now it depends on lambda. but they do not have the same intercept, right? So if you remember, in an equilibrium system, the intercepts here are minus the pressure, and those are now different if I'm thinking of the pressure as the equilibrium version of this, which is F prime rho or F prime little phi minus F. So these are unequal, and so we originally called this the uncommon tangent construction. But the good way to think about it, knowing all that, is the retransformed outcome of a different common tangent construction. And this offset here, you can call this delta p, is a function of lambda, and obviously vanishes when lambda equals 0. You can see here there's a limit to how far you can make this grow. I can't take these tangents past the spinodal point here. That would be ridiculous. Well, I mean, there is a maximum slope on this curve. It's at the spinodal point. So if I just go on cranking up lambda to try to make this mismatch as big as possible, then you wouldn't expect to be able to get past the slope at the spinodal. And indeed you can't. So if I just plot mu as a function of lambda, and it will be the same with reversed sign for negative values of lambda, it basically comes up and then saturates at the spinodal slope. Okay. So now we can think about what this means for the phase diagram and how these binodals now vary. So in the passive model, they are just given by the two usual points. Yes? Well, the reason that I don't want to think of it as the mechanical pressure, and this is a subtle point, I will come back to it actually, but the reason is that this result, the fact that the pressure is the derivative of the free energy times the density minus the free energy, that itself requires that this really is a free energy. In other words, this is the log of a partition function in which there is an h. H talks about forces between particles. And it's because this Hamiltonian is there, ultimately. The Hamiltonian tells you your thermodynamics for your system. It also tells you your mechanical forces. And it's at that very deep level that this pressure, which you calculate just from thermodynamics, is the mechanical pressure. So the problem with what you just said is that in this system, F, the two-well structure of F, looks like a free energy. It behaves like a free energy for this kind of purpose, but there's no Hamiltonian. It's got no relation to forces between particles. It may be related instead to some chemical signaling between particles, which made them have a V of rho that was decreasing. So the link, and I'll say this again later, but the link between mechanical pressure and this object requires a true thermodynamic system, not just one in which all the terms look like they came from a thermodynamic system. So that's an important distinction, and it will matter a lot in active model H, which I hope to come on to in a minute. Okay. So given what I said about the slope, if you increase lambda enough, you expect the phi 1, the coexisting density over here, to asymptotically approach the spinodal point, because that's where the maximum can be. Anyway, whether you expect that or not is what happens. So let's draw a kind of phase diagram. So let's say that first. Phi 1, as lambda goes to infinity, approaches minus phi s, so the left hand of the two spinodals. So that means that the binodal approaches the spinodal. So the regime where you have to nucleate becomes narrower and narrower. So let me draw a phase diagram here. So all of this anomalous phase coexistence stuff, if you remember, it was all about the binodals. The spinodals are fine. There's nothing wrong with those. So these stay exactly where they were. This horizontal coordinate is phi. So I should mark that on in a minute. So this is minus phi s. And this is plus phi s. And these are the binodals. Spinodals, excuse me. So those are the points of local instability, which are set by the change of curvature, when the curvature here is negative, no gradient terms can stop it being locally unstable if you have negative curvature in the local part. And let's get some colors. If I look, I'm now going to draw the binodals. So what I said was at large lambda, this one approaches here. So here's phi b in the minus phi b of the passive case. Here's plus phi b of the passive case. And I have something which actually goes like this. And these don't go all the way to the edge. I'm just exaggerating for effect. Sorry? Did I not write that on? Excuse me. In other words, this horizontal line is equilibrium model B, and it says I have the standard binodals, binodal points just from the common tangent across here. And as I increase lambda, the binodals shift until the left-hand one is approaching the spinodal, and then if lambda is negative, this again, I drew it very badly. This has to approach the spinodal down here. Excuse me for not drawing that properly. Yes. So actually, just to make, and I'm sorry to keep changing this diagram, just to make it a bit clear, there's no reason for this point to have any. I'm just going to move these further out, just to keep well away, because I could be close to the critical point, in which case this is nothing to do with any saturation in what's possible for phi. Okay, so this is a phase diagram. Active model B, and this is a mean field phase diagram, because that's what I was doing. All of these phase coexistence calculations neglect the noise. Okay, so anything more people want to ask about that? Well, you'd usually have A as one of the other coordinates. Yeah, so if you think of A coming out here, this whole thing pinches off to a critical point in A, but at each slice it's pretty much doing this. Yeah. Okay. So obviously one can study this model using a variety of methods, including simulation, and I'm just going to summarize how it behaves. And we did all this about, I don't know, I think it was 2014. And to be honest, it's a little bit disappointing. No, we got our paper into, what was it? What is it? Nature Communications or something. But anyway, let me just summarize the results. Active model B. So one thing you can always do in this model, on models like this, you can look at, you do a quench, you start with the uniform phase, you do a quench, watch it phase separate, watch the domains coarsen. So phase separation kinetics. In this, you expect a domain scale, the domain length, to scale like some power of time. And as far as we're able to tell numerically, alpha is either close to or exactly equal to 1/3, which is as for the passive case. So the active terms have shifted the binodals, but once you go into the two-phase region and you watch it coarsen, you don't see anything which really looks different from the passive limit. In particular, there's no sign of saturation, which is actually one thing we were hoping for long ago. I'll tell you how to mend this later. Saturation means microphase separation. Why might we be interested in that? So microphase separation is when you phase separate up to some length scale, and then you don't evolve any further. So you get blobs of a finite size. Why might you hope for that in a model of active phase separation? The reason is that that's quite often seen experimentally, and the experimentalists normally refer to this arrested or incomplete phase separation as the cluster phase. So no explanation of cluster phase in active colloids. So this has been seen in a number of groups looking at self-propelled colloidal particles. Okay. There's also no explanation of something I'm going to call the bubble phase. So Now, this has not been seen in experiments as far as I know, but it is seen in computer simulations of active Brownian particles with hardcore repulsions. So in ABPs plus repulsions. So this phase, interestingly, you see in computer simulations, is a kind of dual of this. It's an inverse phase. In what you look, if you get phase separation in active Brownian particles on the computer, not always, but often in many parameter ranges, you see holes in the dense phase, which are basically little vapor droplets, and those are also self-limiting in size and don't go away. So I'm going to call that the bubble phase. I will come back to that at least in the next lecture. Okay, so there's something which may be lurking behind this, which again is, when you think about it afterwards, possibly a disappointment of what we might have hoped was a sort of fairly general model of phase separation in active systems, and that's that there's no circulating currents in real space. No circulating steady state real space currents. And there's a really obvious reason for that, and that is curl J equals 0 by construction of the model. At least without noise. So the model, as I set it up, has J proportional to grad mu. So if J is the grad of anything, doesn't matter whether mu comes from a free energy or not, curl J vanishes, and that's the kind of mean field level description. There could be some funny curl in the noise terms or something, but basically, if you wanted to see a big deterministic circulating pattern of currents in this model, you have to look elsewhere. So we will be looking elsewhere. So that's a big drawback, and also that points to what's wrong with this model as a general model, because as a general model of active phase separation, whilst this specific form was strongly suggested by the particular coarse graining of a model we did, where the time reversal symmetry is broken in a term that lives inside the chemical potential, that's not the only way that you can add gradient terms to such a model that will break time reversal, and in particular, we need to think about terms that break this condition as well. So we'll fix that. Okay. Having said all this, I'm now going to pose the following question. What I've said is, okay, I've got different binodals, but all of this looks basically passive. So one might even ask, is active model B active at all? And that's a non-trivial question, because I've always talked here about local free energy functionals and so on. You could imagine that there was some mapping of the equations I wrote onto some possibly non-local free energy that would, under the mapping, would somehow change you from rho to r and would give you an equilibrium model, but in some very complicated other coordinates. And if it's an equilibrium in some complicated other coordinates, it's equilibrium. So that raises the question of, how do you know that a model which you've written down and has some terms which break time reversal, how do you know that those time reversal terms don't sort of somehow conspire to cancel out and make the model equivalent to a passive model? So later, fix these things, fix the model. Now, answer this question. And this is a nice illustration of a general way of deciding whether a model, once you've written it down, is going to be active or not. So it's a little early to break, so I'll go on and break in a few more minutes. So we're going to show it's active. It is active, so that's the answer, via a objective quantification of irreversibility. So for this we're going to need something which may or may not have come up in previous lectures, which is called stochastic thermodynamics. But I've cunningly already laid the groundwork for this in the derivation I gave of the fluctuation dissipation theorem in Model A. So if you want to read about stochastic thermodynamics, there's this wonderful review article by Udo Seifert, Reports and Progress in Physics, 75, 126001, 2012, 800 citations or more since then. This is a big field, and it's one that every practicing statistical mechanics person really does need to know a bit about. Okay, so what distinguishes so now here we're talking here about, well, the question I'm asking really is, let's slightly qualify this question by saying in steady state, because that's the part of the question I'm going to answer. And of course, if it's active in steady state, it's active. Okay, so what we're going to do is consider the entropy production of these equations. So, steady state entropy production, broken chalk again. So, or entropy production rate, and I'm going to call that $. So an S with a bar through it. Theorem. So this is basically comes from, well, this is a core result of stochastic thermodynamics, so although I'll say in a second where it came from before that. Steady state entropy reduction is limit. Some time interval goes to infinity, so I look at the system for an extremely long time. What I do is I look at the log of forward path probability over backward path probability take the ensemble average of that. So this path probability depends on, is from 0 to tau. So it's the probability of a particular evolution of the system over a long period of time. And the question is the system, do movies look the same running backwards? Because if they do, this is going to vanish in a way that I will explain. So if you want to know where this theorem comes from, then certainly you should read this article, but just as a flag, provenance. This is basically a rewriting of various fluctuation theorems, which go by the name of Jasinski, also Joche-Kurchan, and etc., etc., but back further than that. So those fluctuation theorems essentially say that the probability of seeing a process over the probability of seeing exactly the reverse process is proportional to e to the minus delta s of the universe. So if I apply this to a trajectory over an extremely long time, if I'm doing something constantly irreversible, the entropy of the universe is linearly increasing in time. So we're picking out the linear term here. If I missed a 1 over tau, I have, excuse me, 1 over tau average of this. So if my system is doing something irreversible in steady state, this will increase linearly in time. If I take the log, that's what I get. I divide by the time. And this tells me how much the entropy of the universe is increasing with time. And in any equilibrium system, that had better be 0 in steady state. And it is 0 in steady state. And this is exactly the thing which lives inside the detailed balance principle, which has to be 0 in steady state. This is falling off my ear. So I'll just make a note of that. So intimately related to the proof I gave of FDT. In fact, I'm just going to probably just give that proof briefly again by looking at this for Model A. So I'll do this for Model A, and then I'll stop for a break. So Model A, if you remember, is the simplest kind of Langevin equation for a field. No conservation law, everything local. So let's look at this. Model A. So in which I have phi dot equals minus some constant df d phi plus square root 2 gamma kt unit white noise. So earlier, what we showed when we were proving the fluctuation dissipation for this was log pf over pb. We had this expression, beta over 4 gamma. By the time we'd fixed the value of the coefficient so that these two things are correctly related, we have 4 gamma phi dot df d phi dr dt. So that was what we calculated as the log of the forward and path probabilities using the statistics of the noise and the path integral effectively. And this is beta times delta f, where delta f is the final value of the free energy functional minus its initial value. So the point is that the FDT is proved by showing that the ratio of this has to equal the ratio of the Boltzmann factors for the initial and final state, because the product of initial probability times the transition probability has to be equal to the product of the end probability times the reverse transition probability, so that you see the whole process equally often in the forward and backward movies. So that's how we fix this number. So steady state entropy production in this model, which is an equilibrium model, is lim tau goes to infinity, 1 over tau, beta, average over all possible paths of the free energy change between the beginning and the end. And because the free energy is bounded, I can't just have it continuously in steady state. I can't have f increasing or decreasing indefinitely. This is 0. So it's clear why this is 0 in steady state. And in fact, in the steady state system, it's kind of equivalent to a statement of the fluctuation dissipation theorem. So have a 5-minute break, and then I'll do this for active model B, and we'll get a different answer. Any questions? Yeah. Yes.
Why were you expecting at all that kind of microphase separation?
Only because the experiments seem to show it a lot in systems where you have self-propelled colloids with what you might think are mostly repulsive interactions, which was what the original model didn't really describe. I was talking about quorum sensing, but I did say at various points it could possibly also describe MIPS in active Brownian systems like that. Yeah. Yeah.
We are getting binodal in the energy. It's not due to some kind of energetic interaction. It's a matter of fact that velocity is influenced by density.
Well, by the time I've written down active model B, what I showed was how to get a two-weld structure in the free energy-like part from a purely a quorum sensing type interaction. But I could have a two-level model which did come from interparticle forces. I could have a system which actually was going to phase separate and then make it a little bit active. And so then the phase separation would be basically a passive phase separation, but I've still put a term which is broken time reversal in the gradient part. So once I've got this model, this kind of very schematic model, it's a completely open, it's up to you as to where you think the different parts of it came from. So it needn't be, it could be that every term in that, it comes ultimately from activity, which is how it was derived really, but it could be any combination of active and passive stuff in a model of that kind of level of oversimplification. Yeah. Yeah. Yeah, so I've moved the binodals, but the having done that, the behavior looks as it would in a passive system with those binodals. That's just an observation about how the system does behave. And if I have time in the next lecture, I'll say a bit more about why that is. Yeah. Which? This one. Um, well, uh, I don't know any class of systems for which it is disproved. In particular, it was proved for Langevin equations, basically by Jorge-Korsheim. Well, I mean, you have to decide exactly what you mean by this. But if any interpretation where you can read the noise as coming from a heat bath, which is the universe, then this is what you have. Yeah, good question. I still think this is what you have. But I think to say that with the kind of certainty I just said it, I think you need to think of the entropy as more of an informatic kind of the kind of entropy which is in some formulations of statistical mechanics, Jaynes and so on. If you take the kind of Gibbs-Shannon sort of approach to system mechanics where entropy and information are essentially interchangeable, then I think there's no problem with this for active systems. But the fact is that what I'm doing here is proving the system is not passive. So if it would, this would have to go wrong. If this is not zero, then the system cannot be passive. Yeah. Yeah. No. No, what I said is that you could have a model which you construct with all kinds of activity in it and with various terms that break detail balance. Yes. 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 But if I have a system which has no steady state currents and it has and I have a stationary measure, then I can, this is something which John Toner kind of suggested before, if there aren't any steady state currents and I have a stationary measure and I take the log of that and call that a free energy, it may be that the dynamics is actually consistent with a passive system with that free energy. That free energy will typically not be a local functional of the fields. In that sense, if an active system is equivalent to a system with a free energy, then it's got to be passive. In particular, the existence even of some incredibly non-local free energy, quite unlike anything I've written down so far, would be enough to ensure that there's no currents in steady state. So if you like, the deeper thing which tells you the system is not an equilibrium system is that the steady state has some kind of currents circulating, and if there really aren't any, then probably you should be able to map it onto some kind of incredibly complicated equilibrium dynamics, I think. But these currents need not be in real space, they can be in configuration space, and I'll give an example of that later on. Okay, let's resume. Where was I? Oh yes, calculating this for active model B. So this involves a little bit of a possibly doubtful looking vector calculus, but it all comes right in the end. So I'm going to give you the kind of slightly shortened route, which you can check if you want by taking lots of Fourier transforms or something like that. So I'm looking for the steady state entropy reduction of active model B. Here's active model B, phi dot is minus div j, and that's minus, let's write it this way, minus grad. So I'm going to write this again with mu here, bearing in mind that mu has 2 bits, and here's the noise. So that's unit white noise again. So the thing which makes this a little bit more complicated than the calculation for model A is the fact that this is conserved, so there's an extra div here. So I have to somehow undo the div, and that will be the little technical complication we face here. Mu is df d phi plus lambda grad phi squared, and that is my active contribution to the chemical potential. So this is the same as saying phi dot plus del squared mu equals minus 2d, the minus sign doesn't matter, div of the noise. So this is how ordinary model B can be written this way. The only difference is I've got this active term in here. So we do the same trick as we did before when doing the FDT for model A. We say we know the statistics of the noise, so this is an informal way of constructing the path integral for this Langevin equation. Probability of lambda, which is now a vector, some normalization, e to the minus half integral, and this is now mod lambda squared dr dt. So that gives me the probability distribution for phi in exactly the same way as we did before, but I just formally have to invert this equation to make lambda a function of those things. So I have to invert this grad operator. So I'm going to do that in a completely symbolic fashion and then say what the symbol means a little bit later. Yeah. Phi dot is not a vector. Excuse me. You're absolutely right. And my notes are correct, and my blackboard is wrong. Yeah, thank you. Where's the minus sign? Don't think so. Yes, oh yes, you're right. Yeah. Good. So that is wrong in my notes, so I'll just correct it. Fortunately, it's right in the next bit. Okay. So as before, we can just basically calculate the forward path probability from this, as long as I'm prepared to invert the div, which, as I say, is the kind of slightly tricky point, but we know how to do that, and I'll say afterwards. So Pf of phi rt is some other normalization, because there could be a Jacobian in there, exponential minus 1 over 4d integral. Now I'm going to have to start being honest here. Inverse of div phi dot, and I'll say what this means in a minute, minus del squared mu. So this is the correct sign as you had before, squared dr dt, close bracket. So I can think of that as this thing here as e to the minus af. I'm just going to not write all these exponentials now. So that's a kind of action. Here's af 1 over 4d times something I'm going to call funny af. So this is an action density, is basically that. So funny af is this thing. These are mod signs actually, aren't they? Okay. So I can integrate that by parts. In other words, I can equate this to the same thing by partial integration. I can write this in a possibly slightly nicer form, because this is something that does have an unambiguous meaning. Phi dot minus del squared mu inverse Laplacian phi dot minus del squared mu. So if you're uncomfortable thinking about an inverse div operator, by integrating by parts, I've turned this into something with an inverse Laplacian, and that is a completely well-defined thing. That is the Green's function of the Laplace equation. It's an integral against a Coulomb kernel. So let's just say that. So del minus 2 delta function of r prime equals minus 1 over 4 pi mod r minus r prime. So wherever you see this, it means a Coulomb integral. Okay, and now that allows me to define what I actually meant by this. If I want to inverse div some thing, I take the inverse Laplacian of it and then div that. So this is just a technical detail to do with the conservation law. The point is, though, that just like in Model A, there is a way to get the forward and backward path probabilities from the Langevin equation. And they have this kind of structure for the thing which lives in the exponential. Okay, so I've written that down there. So I can write the reverse path probability as well. And the way I do that is exactly as we did before in model A, which is basically just to change the sign of phi dot, because that's the only thing that is reversed on time reversal. In other words, the configuration of phi doesn't change, and everything else in here just depends on the instantaneous configuration of the field. So likewise, AB is, and I'll just write it with lots of pedantic minus signs, phi dot minus. So everything in here has a minus sign now. Okay, so the only thing I've done is change those signs there. So according to that, and when I look at what happened over here, this is, if you want the details, it's on the problem sheet. But you can, I hope, see already what I'm doing. What you find when you look carefully at the expression I had for the entropy production, I can write that as limit tau goes to infinity, average A backward minus AF over tau. A is the integral of these action densities, so I can also write that this way, integrated So I have, just as in model A, I've got to do is look at this difference, and this difference is a quadratic form. It's only the cross terms that don't cancel between the forward and backward. So the cross terms involve things like phi dot, inverse Laplacian, del squared mu. Well, that's convenient because actually I've got inverse Laplacian times Laplacian here. So what you find when you do that is this is negative limit tau to infinity 1 over d tau integral. So actually there's an average in here, isn't there? So there's an average in my log p's, so having taken the log, I can do it like that. Well, okay, that's a little bit of a shortcut, but let me just get to where I want to go. So I'm going to write this in the following way. And then say what I mean by this average in here. So what I've done here, I've looked at the cross terms. I've got things like phi dot inverse Laplacian mu. So the basic structure is phi dot mu. But the bits of that which involve the integrable part of mu, like the mu which comes from a free energy, just give me a phi dot df by d phi, which is exactly like in model A, which gives me 0, because it gives me the initial and final energy, and I divide by tau, and it goes to 0. So the only thing that matters in these cross terms is phi dot times mu a, the non-equilibrium part of the chemical potential. That's the only thing which can give me a steady state entropy production, for obvious reasons, that everything else is equilibrium-like. Okay. So this is quite an interesting structure here, because, okay, so I have this field theory, active model B, and I've calculated the steady state entropy production, and it is a thing which I can find by looking at some dynamical operator of the fields and taking an ensemble average of it and integrating over all space. But this is a spatial integral. So this also, what I'm saying when I say that is that this thing, if I think of it as just a time average, that's telling me about where the entropy production is coming from, which is quite interesting. That's not something which you could necessarily have expected to get from this stochastic thermodynamics thing. In other words, what I'm saying, once you've got this equation, you can read it as an equation for a local entropy production density in steady state, which depends on what the steady state pattern of density actually is, or phi pattern actually is. And so you can talk about entropy production being in certain places. So that, I think, is quite interesting. So let's write this. Steady state entropy production I can think of as this thing, sigma sub phi RT dr dt. sigma phi, now I can think of this as local in space and time if I want to. It's minus 1 over d, some average, well, it's the ensemble average, phi dot at r. So I can think of this as a local entropy production rate. There are some caveats to that, but it's a very useful way of thinking. And this average is over the stationary measure. So I'm assuming there is a steady state of some kind. Yeah. There. No, that would have to be a 1 over tau. Yeah, okay, so yeah, so that's a good point. Yeah, okay, so let's leave it like that. Yeah, that's better. Okay. Yeah, so in the steady state measure, then the time average, is, if you like, has already been done, and this is a function of position. And if I have a steady state like in phase coexistence where phi is not uniform, then this will not be uniform. Okay, and because, as I've just said actually in words, because I might have a broken symmetry, say in phase separation, as I would normally have to do in a system which is phase separated, I have to take the break the symmetry in the steady state measure. So I have to say I do this at fixed interfacial positions, if you like. In other words, if I have a phase coexistence, say with and I have a domain wall that could be in different places, I don't average over where the interface between phases is. That's part of the broken symmetry of the steady state, that there's a dense phase over here and a dilute phase over there, and not the other way around. Okay. And the other thing is that there's still a phi dot here, so that's a bit of a pain, but phi dot, we have the equation of motion for phi dot, and you have to be a little bit careful as to the way the noise term enters here, but it does turn out, since phi dot equals minus del squared mu plus 2d div lambda, it turns out that I can also write sigma phi is minus 1 over d average active mu times del squared total mu. So that's a function only of phi. That's because, as it turns out, the cross piece between mu a and the noise does cancel. And so for details, including that detail. Sorry? This is the total. Plus here. That looks right, doesn't it? Because otherwise there would have to be a different sign there. Good. Okay. Thank you. Yeah. So obviously there's technical details behind this, and they're all in Nardini et al. BRX 7021007 last year. Okay. Right. So now we can talk about this object. So the point is, I mean, to cut to the chase here, this isn't zero. There's nothing zero-ish about that in this model. So the model is active, so rest assured. Now, the reason I proved that was not really because I was in doubt about it being active, but because I think this way of quantifying how active something is potentially very powerful, because you don't have to have, when you write down your field theory, you don't have to have gone through this route of dividing it into pseudo-passive and active pieces and say, oh, well, there's blah, blah, blah. I can just write down any field theory which doesn't respect time reversal symmetry without any kind of classification of terms at all, and push it through this sausage mill. And if the entropy production comes out non-zero, then obviously it's not an equilibrium model. And there have been cases in the past where people worked on models for quite a long time before realizing that actually it was an equilibrium model in some disguised way. Okay. Any questions about that? Sorry, another negative sign. I've got another sign wrong. My signs are all wrong everywhere. Where are we saying now? Yeah, except that that's just changing the sign of a random variable, so that's positive. Yeah. Yeah, that's that's where I'm coming, exactly where I'm going next. Okay, so let's look at what this does. So let's try to take a mean field limit. So I have to be a little careful with this, because there is a 1 over d in that equation. So that's d tends to 0. So certainly, mu goes to a constant in any equilibrium, in any steady state, and in the mean field where there's no noise. So constant mu. And del squared mu is also constant. So it looks as if this is going to be 0, but actually d is 0 as well. So sigma is 0 over 0. So I'm going to have to work harder than that to pull out of this structure what is the entropy production really. So I have to explicitly take this limit and then see what finite or non-finite thing comes out. So must take d goes to 0 limit explicitly. So if I say I have a phase separation, in principle, I can calculate the steady state solution of those equations, which would be the solution of the equations I've found after discovering what the coexisting densities were. I didn't ever give that to you explicitly, of course, and it can't be done analytically anyway. But I can still think of this as phi is phi 0. So this is some disposition of a phase separated or possibly uniform state. And it turns out that there's a square root of d in front of the correction to that. So phi naught, uniform, or phase separated. So the analysis of this is, and this has to be done carefully, and I certainly don't have time to do it now. The analysis of this is in that paper, thanks to Cesare. And so what you find, so the easy thing to look at is the total entropy production, but it has a suggestive structure, which is completely consistent with what's written down over there. Spatial integral of it. So I'm going to write it this way. C1 times the interfacial area. So I get a term which is a contribution from interfaces. That's not very surprising, because that's where mu a is non-zero and where del squared mu is non-zero. So that, you'd think, as John said, that's only going to happen where you have interfaces, because if mu is uniform, then there appears to be nothing there. But there's also a second term, C2d, and I'm being crude about this, but I'm just saying volume of system. So this would then depend on how much of the two phases you have. So this is order d to the 0, and this is order d to the 1, obviously. So this order d to the 0 term is proportional to the interfacial area, and order d to the 1 is a bulk. So there's physics in that. If you look at this thing, if you take the limit carefully, this has an irreversibility which is sort of deterministic. It doesn't require noise everywhere that you have an interface. And that's, you know, having you can think of that just in terms of mu a. Mu a is lambda del phi squared. This is big at an interface, and there's no reason for this thing to vanish there, even as I take the limit of turning the noise off. But then there's also, in the bulk, I have fluctuations. So in both bulk phases I have fluctuations. And those fluctuations, if I looked at them closely, would not look the same running forwards and backwards. That's what this result is telling me. It's telling me that the noise-related part of the density profile is itself giving me a steady-state entropy reduction, which obviously then that does vanish as I turn the noise off, unlike the interfacial contribution. So. Well, no, I have to take that limit. It's actually d to the naught. Because if there were really no fluctuations, so I'm saying that these things are big near interface, but that it would still be 0 if there was no noise at all, because mu is uniform. This is a very good question. A very good question. If you think about the anomalous phase coexistence, if you thought of the system as suppose you imagined that the free energy part really was a free energy. So suppose I had a system which was doing a proper equilibrium phase coexistence, and then I'd give it a little bit of activity in the lambda term, and I find the phase coexistence has shifted. What can that mean? That has to mean that somehow that lambda term is effectively like a pump across the interface. It has to be sustaining a difference in the bulk densities, even though this term is only there at the interface. So it has to be pushing a flux across the interface, which then somehow a diffusive current is balancing. So I haven't shown that. I don't even know really how to prove that, but something like that must be what's going on. Well, okay, so if you look at the interfacial behavior in ABPs, at the interface, that's where you get a region where particles are sort of stuck and all pointing the same way. Now, I think it probably is true that if you then kind of draw a little box there and start running movies forwards and backwards, you probably would see a big difference, but I've not actually gone through that mental exercise, so I'm not quite sure. Yeah, good question though. Okay, so let me just summarize what I said in words to John. In bulk phases, S comes from noise, so from fluctuations. At interfaces, so in phase separation, order d to the naught from interfacial regions. Okay, and if you want more on that, see that paper. So, as I said, this illustrates the method for quantifying irreversibility, and it doesn't need saying now, but the result to my original question, yes, AMB is active. But as I was sort of saying over here, turns out to be a little bit boring. Okay, so that means that there are, and as I just discussed answering Irene's question, there must be some non-trivial steady state currents going on, but they must be in configuration space. They can't be in real space because of this curl j equals 0 stuff. Okay, so I'm going to correct the curl j equals 0 stuff in a bit, but in the meantime, I want to go a little bit further in the same direction and think about coupling this model to a conserved momentum. So that's active model H, and this will distill a number of things which will come up in questions, so that's quite good. So, what was model H? I had the same structure as usual, with a convective derivative here. So I'm going to write this as a deterministic flux and yes. Well, I should write it like deterministic plus a noise flux, if that's okay. And then this involves the unit white noise and the square root of d as usual. So the deterministic part here, jd, is minus grad df d phi, and that was model H as I defined it passively as before. So I just have, in the phi term, all I do is I have to add the extra convective derivative here, and this is still the usual diffusive current over there. So the deterministic part of that, I'm now going to add my active term to lambda grad phi squared. Okay, so this is the TRS breaking term. So this is just the advected version of what I've been talking about up to now as active model B. And Navier-Stokes. So that P is whatever's needed to give me div V equals naught. So this is a proper mechanical P. It's got nothing to do with the kind of pseudo pressures and funny things that I was talking about before. And there's going to be a div sigma, as usual, div sigma phi. So so there's some stress here coming from the order parameter, and in general this is going to have some active and passive bits. And what I showed before, oh, actually it's on the problems, I didn't really show it, but I told you it. If f is a free, so this comes back to the question that was asked up here earlier. If the thing that I was calling f in the free energy part in active model B, if that really is a free energy, then I know what the stress is from that term. So if f is really a free energy, the bit of it which comes from f is minus phi grad mu. And I might have to add something active to this. And there are other ways of writing that. But the point was, as I said in answer to that question, the way I'm building these models anyway, so f incorporates everything of passive form even if active in origin. So this did come up earlier. In MIPS, in active phase separation caused by quorum sensing, for instance, the very existence of two minima in the effective free energy is because of activity, not because of interparticle forces. This result only holds if that F comes from a Hamiltonian, and therefore the interparticle forces which determine the phase equilibria also determine the stress, because that's where stresses come from, right? So in an equilibrium system, you have a relation between the free energy and the stress tensor, which comes ultimately from the fact that there's a Hamiltonian behind. If I construct something which looks exactly like a free energy but comes from some totally unrelated physics to do with communication between bacteria or anything like that, then this is going to break. So let's write this here. So this leaves us in a bit of a tight spot, I have to say. No link. So the cases where there would be a link, which also came up in questions, is if I had a system whose phase coexistence was basically passive. In other words, you had particles with, say, attractions, and then you put a little bit of activity somewhere, and so you get a term which breaks time reversal in what was otherwise a properly passive system all the way through. Okay, and there's something which you will, of course, realize I've not mentioned yet, and that is the kind of stress that you get in this equation when you have active particles. So there's an additional thing which I've not mentioned. So if I have a solvent with swimmers, and this did come up, of course, in several other people's lectures, but also in my own overview when I was looking at the active pneumatic model, I have a stress sigma A. So I wrote this involving Q. If I have a polarization field, there's some activity parameter P. That's true here as well. So P here is the swimming direction of a particle. And at first sight, this might appear to be an embarrassment because I don't have a P in my theory. I don't have a polarization, because I was quite careful at the beginning to set the whole thing up where the only order parameter is the scalar density, right? So can I deal with this? Well, it turns out that I can. So, and to get some motivation for what this should do, I can refer back to the derivation that I gave you of the quorum sensing model, where in fact I did have a P, and then I adiabatically eliminated it. So let's just drag back out from that derivation. What is the relation between P and phi which allowed me to eliminate it? There's a steady state condition which allowed me to write P in terms of phi, and it's this. P is minus V naught rho. So this was, of course, in terms of rho, because I only ever was talking about this in terms of the density. I didn't do the kind of model B stuff on it. But you can see the structure. For a scalar field, the default behavior is that the polarization is proportional to the gradient of the scalar, which is kind of obvious. It's a local vector. That's the only local vector I have left, having done all this coarse graining. So that's okay. It's interesting, though. It says that this stress also is something which is going to appear primarily at interfaces in the scalar field theory. Yeah. Yeah, now that's interesting. Yeah, so you say that there could be some direct link between P and V locally. I think it couldn't be that, because that's not Galilean invariant. So you'd have to have to grad V. You could have. Yeah, but you couldn't have something which was just directly involved V. Yeah, so Galilean invariance knocks out the term that you just suggested. Yeah. Okay. Sorry. Okay. Yes, because it might as well be just in a moving frame. Yeah, yeah, yeah. Yes, but then that's not a vector. So you'd have to think of something that you can make out of gradients of V that is a vector, and you'd probably be higher order than V then. Yeah. Okay. Yeah. This one. That's problem 1. So in the, I did state it for the passive case. And yes, I mean, there's just a little trickery to get to that. I mean, I could write down, by the way, I could write down an explicit thing here, whose divergence is that, but because it's only the divergence that enters the equation, this is a much neater expression. But yes, okay, that's where that comes from. So if you like, there's an active sigma. Let's write this sigma A. Well, it comes from phi, so I can think of that as the active part of sigma phi or whatever. Let's put a free energy part there. And this is going to be, and this is of course a different zeta, but it's still just a parameter, grad phi. So outer product of two vectors, that's the active stress in a scalar model. Okay. Yes. Spoiling the steady state structure, you think? That's interesting. That's interesting. So you're saying once I've coupled it to a fluid, if I don't still have that, you're saying, well, maybe the phase equilibria don't work. That's an interesting question. I've not actually thought through that, in fact. Yeah, okay. Yes, I would have to think carefully about to what extent that's true. Good question. Okay. Right. So just in the last minute or two, I want to just say roughly what this does. So I'm going to cut corners here because I don't have time to go into detail. Actually, interestingly, if I do look at, if I explicitly construct this object so that its div is equal to that, this mu has gradient terms in it. Inside mu, there's a minus k kappa del squared phi. And so there has to be part of this which involves grad phi. And actually, it's of exactly the same form here, but it has kappa in it. It has the square gradient coefficient of the free energy. So this is a term which is already in the form of that term is already in here. So let me just say something about that. So again, this is just kind of information. Let me just say this. Note, sigma f phi, so the equilibrium part, can also be written this way. This is actually the osmotic pressure, or it's f phi minus phi, so I absorb this into P anyway, delta ij. So this goes away. What is it? It's phi f prime minus f. No, it's not. It's okay, there's an isotropic term, but the gradient piece of this looks, or the non-isotropic gradient piece of this actually is also like that. So in fact, the active stress resembles the square gradient bit of sigma f phi. There's a key difference though. Kappa is positive. Zeta can have either sign. So actually the physics of this term is very interesting. If I have any kind of ordinary, vaguely equilibrium-like structure here, which is not necessarily the case, but let's suppose we do have at least something of this left, then that zeta is like changing kappa, and what's more, I can change kappa to make it negative. Okay, so this, what happened to it? Yes, well, then that is also an exercise. You actually, if you take the div of this, that is what you get. It isn't immediate. I mean, it's not immediate. You have to do some work on it. This has there's stuff in here. So the osmotic pressure also has gradient corrections, but they're isotropic. So this is the anisotropic bit of the equilibrium pressure with K there. Yeah. Okay. So I'm conscious of the time. Let's just okay. Let's just. I'm just going to very quickly summarize what happens. So for zeta positive, so that's extensile. This acts. So this sigma A acts like an extra surface tension. So I can think of that in the following way. I've got swimming particles. So here is such a particle. And in the extensile case, it's grad phi says that it's oriented normal to the surface. P is twiddles grad phi, could have either sign. Either way, this is an extensile particle whose swimming direction is normal to the surface because that's what grad phi is. So if you look at that flow field, you can see why that's like adding to the interfacial tension. It's pulling stuff inwards along the interface. Okay, so the flow or the active stress contracts the interfaces. And, well, you can guess the punchline. If I take the other case, contractile, effectively negative surface tension, or at least contribution to it. Okay, so next time I'll pick up and just spend a few more minutes on what that effects of that can be, and then I'll turn I'll switch off the hydrodynamics again, go back to Model B, and fix up some of the faults that I said were there in active Model B in terms of things that should be happening which it doesn't capture. Okay, thank you. If there are more questions, of course, but I'm sorry I'm late.
Group photo-wise,
Yes.
staff advised us to do it at 12 so that the sun is less